Our speaker today is Gordon Moore, who is chairman of the board of Intel Corporation, a major supplier of microprocessors and other useful things. And he's going to talk today about VLSI industry trends, technological and economic. Gordon?
Okay, well, thank you. I'll hide over here behind the lectern to get out from the way of my own slides. This year, the integrated circuit is 30 years old. It's old enough that I read in the paper last week that TI is getting their patent issued in Japan finally. I am repeatedly amazed at what we can design and build. You know, I've been involved in this industry since the beginning of the integrated circuit, in fact, before that. But not long ago, I would have had a difficult time accepting the fact that we could either design a 1,000,000 transistor circuit covering a chip maybe a half a square inch, or that if we were able to design it, that we'd be able to make it. Now we not only expect to be able to make such things, but we expect to be able to make them so they work the first time. We've really come a tremendous way in this 30 years, and I think it's fair and perhaps appropriate to ask, is the technology getting anywhere near saturation? That is, are we going to be able to continue the progress we've made in designing and making the integrated circuits as the technology becomes fully developed? And we could ask, where is the technology likely to go? Technically or geographically, I suppose. And even what drives it. So today what I'm going to do is stand back and take the 20 or 30-year view of what's been going on in the industry and try to make some broad extrapolations and hopefully draw some conclusions about what is happening, what has happened, and therefore maybe we can figure out what might happen in the future. First, I think it's useful to sit back and say, what's made this technology so powerful already? Clearly, it has had a very important impact and has been able to evolve rapidly for 30 years or more. And I think the reason this has happened is we've been exploiting a violation of Murphy's Law. By making things smaller, everything gets better simultaneously. Essentially, you don't trade anything off. You know, the things get faster. The electrons don't have so far to move. Clearly, we can cut the power consumption. The systems made become more reliable because we can go to higher levels of integration on a given silicon chip. And we've been able to keep the reliability per silicon chip at least constant, irrespective of what we stick on the chip. But most important, as we've progressed along higher levels of integration, we've been able to make things cheaper. Now, the cost of doing things electronically in the 30 years since the invention of the integrated circuit has dropped 1,000,000-fold in many cases. The easiest place to see that is you can buy a megabit DRAM today for less than Fairchild sold its first individual silicon transistors for 35 years ago. I remember those first transistors. We sold them for $150 a piece. Now a megabit DRAM that not only includes well over 1,000,000 transistors, but all the circuit design and interconnections that go along with it sell for far less than the same thing as the individual transistor. I've often used an analogy about this. You know, what would have happened if the auto industry had advanced that rapidly during these last 30 years? And you come to the conclusion, you know, 1,000,000 miles an hour, 500,000 miles to the gallon of gas. It'd be cheaper to throw away your Rolls Royce and buy a new one than to park it downtown for the evening. But of course, you wouldn't have to throw it away. Its reliability would be such you could pass it on for several generations. Well, I thought this was pretty good, though one time somebody in the audience pointed out to me it'd only be 2 inches long and a ½ inch high. It wouldn't be much good for my morning commute. But I think as you look at an industry that's decreased the cost of its product 1,000,000-fold, what one characteristic does that industry have to have? it has to sell a heck of a lot more of them at the end of that time than it did in the beginning. We clearly have to sell a lot more than 1 million times as many transistors today as we did 30 years ago to make up for this. So I think that's the slide I'd like to start with. In a lot of respects, it's going to be the most important slide I have concerning what's been required to make this industry go. And that is my curve of market elasticity. And I'm going to generally be looking at the same time scale as we go through the various slides, about the last 20 years, which coincidentally matches Intel's history. We were formed in '68. But if you look at this estimate of the total number of transistors produced in the world, you see that it is on a curve that goes up a factor of 10 about every 3 years for the average slope in there. A factor of 10 every 3 years. If it doubled every year, it would be a factor of 8 in 3 years. So the amount of transistors the industry builds more than doubles every year. You all know the nature of a series that does that. It means that during this year, we will build more electronic function than existed in the world on January 1st. It's a phenomenally elastic market, more elastic than any other one I've ever been able to see. Now, I got a little chicken on the slope up here at the upper end, because frankly, it gets increasingly hard to identify applications that use 10 to the 15th transistors per year. That's 1 million transistors for every man, woman, and child in the developed world. It is really a phenomenal amount of electronics. And I think you people have probably all used your 1 million transistors and then some this year. But you have to look forward to 2 million next year, 4 or 5 million the year after, and so forth. And you have to bring all your friends from the liberal arts division along with you if we're going to keep on this curve. I used to have a difficult time generating points for this. I had to go down through all the products made, estimate how many transistors I had, and add them up. And I probably could get precise within a factor of 2. In recent years, all I have to do is count the number of DRAM bits and multiply that by 2, and I'm well within a factor of 2. It turns out it's gotten easier rather than more difficult as time has gone on. Well, let's look at a few other trends. One that we alluded to earlier is the fact that we continually make smaller and smaller structures. This has been on a quite good exponential curve with a slope of about a factor of 2 every 6 years. And I could actually extrapolate that back another decade, and it would still be on the same slope. Every 6 years, we can cut our minimum dimensions in half. And it has continued without any real sign of saturation. Now, saturation has been predicted in this curve about every 2 years for the last decade or more. We didn't think we'd get anywhere near a micron optically, but in fact, we not only got to a micron, we now expect to use optical lithography techniques to at least to a half a micron and probably to 3/10 of a micron, and clearly well beyond my retirement. It is amazing how this limit has continued to recede as we've pushed further and further to make the smaller structures. We've decreased structures 100-fold in dimensions without yet approaching any kind of a fundamental limit. There's some indication that maybe around 1/10 of a micron for minimum structures we'll start to see some effects that will make life more difficult, but for the time being at least, we think we're on this track of continuing to make things smaller without any real problems. In the other direction, we've had a similar trend toward making structures thinner. In a lot of respects, this one surprises me significantly more than the narrower lines. I expected we'd be getting in significant problems when we got the film thicknesses of the order of 1,000 angstroms. I felt that 20 years ago at least. Because on the back of an envelope, you can convince yourself that if these films come down as statistical piles of atoms that you start to see huge variations in the thickness when you got down to that kind of a range, so the electrical properties wouldn't behave well. But this clearly hasn't happened. Working on down to films below 100 angstroms in thickness, I got a little aggressive on the curve out here at the tail end. We don't work much below 100 angstroms these days. Where you only have the order of 10 atomic layers, these things still behave beautifully. No signs of the kind of statistical holes that I thought we were going to get. Now, clearly, it's not a random phenomenon. The forces on our side, chemical forces in this instance, and these things actually tend to work in our favor rather than against us. Again, we're trifling with Murphy, I think, in the way this goes. Here, though, we actually are approaching a limit, and on these thin films, we're down at the point where we can actually see quantum mechanical tunneling through them. Instead of that being a problem so far, we've exploited it in some of the electrically erasable memories, but we can't expect to go an awful lot further on that particular limit because we're actually starting to reach a fundamental limitation. Taking another cut at it, we can look at the charge necessary to separate a 1 or a 0 in several generations of EPROMs in this case. It's unusual. You know, I count transistors by saying 10 to the 15th. I count charge by saying 100,000 electrons. This is the opposite way we would have talked about things 20 or 30 years ago, where charges that we dealt with were 10 to the 15th electrons, and the number of transistors were down in reasonable numbers. But here again, we have a trend that has remained quite constant. We cut the charge about a factor of 2 every generation of memory products, and show a little sign of it rounding off. Now, we're up to the 4 megabit EPROMs these days, and I'll admit I didn't update my curve to see if we're still on this, but I'm sure we're well under 100,000 electrons on the stored charge. And in spite of that, we still expect to get a 100-year retention of this kind of a memory, longer than we ever would have committed a decade or more ago. Let's take another one of these. Let's take DRAMs. And here, the world hasn't been quite so uniform. We were coming down the same kind of a curve until the 64K DRAM, when all of a sudden we ran into a problem. The memories were forgetting a bit now and then. Big systems built out of the initial 64K DRAMs tend to make soft errors, non-repeatable loss of data in the memory. And this was tracked down after rather extensive investigations to being the result of residual alpha particles coming out of the packaging material. One alpha particle made enough whole electron pairs that could actually erase the data in a DRAM bit. Of course, there are a lot of solutions to that. One is to clean up your packaging materials to cut the incidence of alpha particles. The other is to try to put some kind of a layer on there that absorbs them. Those things were done. But in addition, we had to jack the number of electrons back up so they were not sensitive to a single alpha particle error. And now it's flattened out at around a million electrons necessary to be sure you're not going to get a problem from a single alpha particle. This is the one place I can identify where we've actually run across some kind of a relatively fundamental limit that we had to live with. It's also the reason that the DRAM technologies have gotten so darn complex. You can't continue to scale the capacitors as time goes on. You have to go in there and figure out how to get enough capacitance in the small area. So people are going to three-dimensional structures with deep trenches into the silicon and things like that in order to get a capacitor of sufficient area to get your million electrons on there so we have alpha particle insensitivity. I think had it been any product except DRAMs, which is the macho product for the semiconductor industry, we would have relaxed and enjoyed the technology we had available and stopped at a much lower density than we're still fighting to achieve on the new products today. Well, let's turn in a slightly different direction and look at another technological trend. And this is what's happened to our defects during this time period. This is a very important change in that we've finally worked ourselves out of a rut. We used to develop a technology, stick it into manufacturing at relatively low yield, or relatively high defect density, massage the process and the product until we got higher yields. Just about the time we were doing pretty well, 20, 30% yield, we'd find we got an economic advantage by scaling the geometry, which redefines the defect. Smaller ones now affect you. Going back in again at high defect densities and low yields and working ourselves around that loop. Made a lot of progress that way, but we were changing generations of technology as fast as we were decreasing defects, so we didn't make any real progress for a while. The last couple of generations, we've broken out of that. We're starting at lower defect densities and taking them down to much lower defect densities. And this, of course, has significant implications on what the designer can consider in terms of chip size and so forth. We can make very much larger devices today than we used to. In fact, today it is an occasional event, at least, to see a perfect wafer. That is one where every circuit on it is good. I have Intel's first 100% yield wafer hanging on my office wall. I've heard rumors of competitors having 100% yield runs, where every wafer in the run was 100% yield. I'll have to admit, I've yet to see one of those. But 100% yield wafers are something that would be hard to conceive of looking back at, say, the mid-70s. So a tremendous amount of progress has been made there. And I think it really means we can seriously consider things like wafer scale integration, where the whole wafer is built into a system, should there be another good reason for doing that. As a result, our chip sizes can get bigger. And they've grown about an order of magnitude in area over Intel's history, as well as increasing 1,000 times or more in complexity during this time period. So we now have an allowed range of product complexity, and here I'm really on memories, taking logic circuits, for example, where you can make anything you want that falls in that red area. So million transistor kind of logic circuits now are straightforward to do. In fact, we've introduced a few of them this year. The next generation, staying on this curve, will look at 4 or 5 million transistors in the next generation of microprocessors. And I don't see why we ought to be falling off this curve. And if you extrapolate this to the year 2000, you conclude that we can be looking at a logic circuit with something in the 50 to 100 million transistors on it. It actually extrapolates closer to 100 than it does to 50. I don't quite know what to do with 100 million transistors worth of logic on a chip yet. I think every logic function we've ever built could be put on one chip with this level of complexity. And I think it really is a challenge to figure out what to do with it. But this challenge is not new. I picked a slide here, which I have on its side, but you can rotate that 90 degrees. This shows the design effort versus time to make the state-of-the-art logic chips over a period of time. And I actually used this slide in a solid-state circuits conference keynote address, I think in 1979, showing that we were having the problem where the cost of designing these things was absolutely skyrocketing on us, and something that we weren't going to be able to continue to live with because the investment was going up so dramatically. In fact, at that time, and actually for somewhat longer than this slide shows, this curve should have come out here a ways before it fell down. It was taking about a constant effort per transistor in the completed circuit to design it. This is kind of the hardware equivalent of the productivity of a programmer being so many lines of code irrespective of the time. We had the same kind of a problem in the hardware area. We get about the same number of transistors designed per day, per person involved in the design. Now this was still pretty darn good. This took a lot of computer aids and one thing and another to stay at that, because it would be easy to imagine the design effort would go up with some power function of the number of transistors. But with CAD and systematic design technology, we've been able to overcome this now and get to the point where for only a slowly growing size design team, we can make increasingly complex integrated circuits. This really lets us use this processing technology that I showed in the previous slide, so we can actually fill that entire red area on product complexity. Well, moving in another direction, and this one of all the slides I'm showing doesn't have real data in it. It's just my guess of what's happening. That's the growth in the number of different semiconductor products. With the ASIC technology that's gotten pretty widely distributed and a lot of systems designers making their own circuits now, we've had an explosion in the different functions that are out there. This has a lot of implications for the manufacturer. It means each one of these can't be considered a separate product and put through its own separate reliability testing, for example, because there just is not enough capability to handle that. We have to qualify generically the process. Similarly, the designs have to work the first time, so we have to kind of qualify the design technology rather than go through and exhaustively try to test each of the products that comes out. I think it's a real control problem and one that has a significant impact in the industry, although less impact directly on the users than do a variety of others. Moving to another trend, and I'll get down to the processing technology. Our processes have continued to grow in complexity. When I look at this, it's hard to realize that the principal initial argument for MOS over bipolar was the greater process simplicity. It only used 4 masking steps instead of 6. We've sure succeeded in changing that over the years. Here I picked some EEPROM processes here on this particular curve. We're getting to the point now where new processes are of the order of 20 masking steps. The new DRAM processes are on that level of complexity also. The logic processes with 3 layers of interconnections tend to be in the high teens. We really have succeeded in making this a lot more complex. And of course, masking steps are only a good proxy for the total process complexity. Each of these usually requires a deposition, a masking, and etching, some kind of a heat treatment, probably a half a dozen or more major process steps for each mask. These things have gotten tremendously complex, but even during this, the defect density has dropped dramatically. What it gets tied to, though, is a tremendous increase in the cost of developing another generation of process. And this actually was the Intel data. In '68, we started out, we developed 2 major new processes as well as our initial products and put them into production for less than $3 million. Our latest process is the order of $60 million to develop and get running in production. The one difference here is that I'm now including some of the engineering necessary to get to high yields. Looking at that curve, would anybody want to guess when the Japanese started to become important in this business? You're right, it's right there at the knee of the curve. We really took off. And it has gotten exceedingly difficult to get a leadership position in the industry based on the processing technology. This is kind of qualitative data also. But if you assume that the industry leaders, the people that generally have the top products out there, you know, let's say the half dozen companies that are more or less parallel in technology at any time, spend 1 unit on getting their position. If you wanted to try to get a year ahead of that, we estimate it would take probably 3 times that expenditure to do, just to pull everything in that far. You know, there you have to develop a large portion of your own equipment. You have a lot of additional loads that you take on yourself that don't exist if you're going along generally with the leading edge. The net result is nobody has a year's lead anymore in general on the technology, maybe on some particular part of it where they've invented a new structure, but not in the mainstream technology. And if you want to lag behind a couple of years, you can do it very cheaply. You can pick up what other people did, and that's been a viable strategy for some of the companies in there. But the point here is that where a major portion of the industry's advantage used to be in sustaining some kind of a technological advantage in the processing, that has gotten very, very difficult to do, and it's hard to see any sustainable advantage there anymore. So increasingly, we try to be competitive on the processing technology and get our advantage in the product design in order to maintain a really viable business. Well, other parts of the business have gotten more expensive also. For example, if we look at the cost of various pieces of equipment, these are several major pieces of equipment. You see, their costs have grown roughly on the exponential scale during this time period also. When Intel started in '68, a given piece of equipment cost about $12,000. You could buy a lithography machine or a bank of furnaces or a sputterer. It was around $10,000 or $12,000. In the 1 micron generation, it was closer to $1.2 million. It had gone up 100-fold in the cost of a piece of equipment. In the next generation, we're looking at pieces of equipment that individually cost $2 to $3 million in several cases. Now, the discouraging part of this is the throughput of these pieces of equipment is about the same in 1968 as in 1988. They still get their 20 wafers per hour through, or whatever the nominal number is. The only real difference in the output is that the wafers are bigger than they used to be. So the cost of the equipment has grown dramatically, so the business has become a lot more capital intensive during this time period than it was 2 decades ago. A significant semiconductor plant now, one to make volume products, costs about as much as a significant steel mill. Our Albuquerque plant, which is 4 different processing modules, by the time it's filled, will cost well over $600 million for the building plus the equipment it contains. I say well over because the last couple of modules aren't yet committed, and each one is sequentially costing quite a bit more than the previous one. The net result is, if you look at the cost of a facility that is reasonably well balanced from a production point of view, this is the cost of capital to process about 1,000 wafers a week. A minimum balanced facility, that is where one piece of equipment isn't kept waiting because it has more capacity than the other, is probably a couple of thousand wafer starts a week. So a reasonably competitive manufacturing facility has to have about $100 million worth of equipment in it at the current generations, or the 8/10 micron generation that's just moving on into production, and would probably have more than that to get better utilization. If anything, the 1/2 micron generation is significantly understated in this curve. So, you know, the first thing you see, seeing how capital intensive this was, that this is clearly not a business for startups. So we look at the new semiconductor company formations over this time period, and we see, well, it may not be a business for startups. The people that finance startups didn't realize this during most of this time period. By the way, this curve has some other interesting things on it. It shows you the dates of the changes in the tax law. This was the introduction of the 1969 tax law, which is a significant increase in capital gains tax. There was the '79 tax law change that decreased the capital gains tax, and then it came back again in the '80s. It's probably understated here at this end because you don't pick up all of the startups in something like this, because some of them are invisible for a few years before they're picked up. So in spite of this capital intensity, we had a huge increase in the number of semiconductor startups. In fact, we can integrate that. I'm just out of phase with the lights, I see. And this is a pretty good measure of the total number of semiconductor companies in the world. It did a little bit more than integrated that. I added in the foreign companies, but in this curve, they don't make much difference because they're lost in the noise of all the US companies. And I accounted for some of the ones that went out of business or were combined with others. So we have an industry here that has something over 200 companies involved in it, most of them US companies. And something like that is clearly a highly fractionated business, you might think. But if you look at it another way, you see that, in fact, the business is done principally by a relatively few companies. Here I took MOS LSI instead of the total semiconductor industry. They're not very different in this curve, but you see that something approaching 70% of the dollars, say 2/3 of the business, is done by the top 10 companies. And 30% of it is actually done by about the top 3. So you have an industry here that has a lot of little companies, a few medium-sized companies, and a very few very large companies. So it looks like an industry viewed at this level that is dominated by this 10 very big companies. Well, that's fine, except if you look one step different and look at the 10 companies, the thing you see is they're not the same 10. Now, this is color-coded on this slide. The blue companies are US-based, the red companies are Japanese-based, and the green company is other. Of course, the trend you see here is the graph, or the table gets a lot redder as you go to the right. And you might think this is terrible performance on the part of the US industry. Well, take a particular example, or let's take Texas Instruments, for example. They went from 65 million to 238 to 572 to 1,271 million in revenue during this time period. Now, this is really a growth that most companies would be extremely happy to have, growing, what's that, 20-fold over the 20 years. You know, unprecedented in most other industries. It was good enough to go from first place to 8th place in this case. In these 5-year periods, with one minor exception, the 10th largest company is bigger than the largest one was 5 years previously. So it's been a phenomenal growth industry, but the real rapid growers have turned out to be the Japanese companies. Now, I expect that this will continue to change because there are a lot of other people who are trying to get in to the 1993 version of that. You know, we have at least 3 major Korean companies that are aggressively pursuing this. I suspect, in fact, Samsung will be in the top 10, if not next year, the year after. Certainly by the 1993 update I do with this plot. You got companies like Philips and Siemens in Europe who are strongly dedicated to a major position in the semiconductor industry. You have new entries coming in from some of the developing countries. Taiwan is aggressively going after this business. So I think we're going to continue to see a lot of changes of the players in this top 10. And those of us who are there don't want to get pushed out very easily. So this has been a broad overall view of some of the trends in the semiconductor industry. You know, we looked at some that were technical, some that were financial, and some that are structural. I think overall, it's something that really has shown phenomenal progress over this period of time. In fact, it's unprecedented in its rate of change, as near as I can see. You know, the million-fold plus decrease in the cost, combined with the fact that a technology that didn't even exist when most of you were born has become so important in this 20-year period. It's really been an exciting roller coaster ride, but might take a look at what it's going to take to keep it going like this. And I kind of see 3 things here we have to worry about. One of them I'll call driving the machine. You know, this business and its rapid growth continue to depend on the market expansion in order to be able to afford the investment to keep the technology moving. You really have to look. Have you used your 1,000,000 transistors yet this year? Now, this is the question it comes down to. Where do we find applications for 10 to the 16th transistors a year or 10 to the 17th transistors a year? So how can we use this much electronic function? I think we can wave our hands and see some things that could produce the kind of requirements we're after there. You know, the real-time speech recognition is one of my favorites, so I can talk to my PC instead of having to fumble over the keyboard. That can use more bits and MIPS than about anything I can think of. But those are the kinds of things you have to have. In order to use these huge numbers of electronic functions, you kind of have to come up with an application that you can multiply by the population of the world or by the number of households in the world or something like that. It can't be something that sits one per major university and have any real impact on keeping the industry driving through these very high volume applications. And I will admit, I am having trouble seeing the applications that are going to consume the vast amount of electronics we have to make. But that shouldn't bother you. I've always had trouble figuring out who was going to use all of these things. I gave a talk a decade ago, roughly. Essentially, that was the subject of the talk. Who's going to use all these functions? Well, I thought I was talking to a technical audience. It turned out there were some security analysts in the crowd. And they got very concerned, you know. So the last thing you want to tell a security analyst is, no, what are you going to do with all the product you're going to make? So I got the job of having to answer that question for the security community at a subsequent talk. So using the same kind of argument, you needed something you could multiply by a big number like the number of people or the number of households. I decided I'd take my house as an example. And I'd walk through the house, room by room, and try to identify every application I could think of for a microprocessor. This was 77, 78, kind of that time period. And I went through there, you look at every light switch, and yeah, I could use a timer in there, I could use that, and the washing machine, and so forth. I think I identified 80-some, 85 or 87, I forget which, possible applications for a microprocessor in my house. Well, I can go through there now, and I don't have that many, but I'm sure that there are several tens of microprocessors. And well over half of them are used for applications I never thought of when I went through only that long ago. These low-cost functions create a lot of their own applications, and I hope we can find some more that are of the size of the PC in order to keep driving us along this exponential. But the nature of exponentials are such that you always fall off of them. Any of these extrapolations of an exponential produces a disaster. I remember as a student the extrapolation of the growth of the population of the world. You know, pretty soon you have one person for every square yard, then every square feet, and then you go 3D. And you know, where is there really a limit? And finally, one of the physicists in the audience said that the one limit he could think of is when you had a ball of humanity with the periphery expanding with the speed of light. And it turns out you don't even have to extrapolate very far into the future to get to that point when you pick an exponential like that. So we are going to fall off of this one before too long, I'm sure. Anyhow, at this stage of the game, it's easier for me to extrapolate the technology that's going to serve these markets than it is to see these markets for 10 to the 16th or 10 to the 17th transistors per year. And I have a concern that when these markets do occur, they're going to happen in geographic areas where we don't have as good an access to the market. You know, we can serve our US customers very well, our European customers pretty well, most of the Asian Rim quite well. Japan, we have a tough time getting into, and that's a major part of the market. So there are problems for the industry overall, and some additional problems, I think, for any particularly geographically located company. Next thing is driving this machine is keeping the wheels on. It is not running across anything that's going to really stop our rate of evolution. I don't see anything happening here, but the kind of problem we ran into in DRAMs where something came along and bit us that we didn't expect. Now, I've been expecting something like this to come out of the blue for some time. I remember a paper published back in the early 60s that predicted that the reliability of electronics would start to decrease when the active volumes got smaller than about a cubic micron. The argument was that cosmic rays would ruin material and over that kind of a dimension. And there are enough cosmic rays coming in that this could be significant. Now, our active volumes are well below a cubic micron of these devices, and we haven't gotten bitten yet. So that may have been a false prediction. Now, I'll admit I haven't gone back to read the article to see if I could find a flaw in it or not. But something like that is likely to come along that will significantly slow our rate of evolution. The other thing will be if we just can't figure out what to do with the things. That is, if the need for very complex functions cannot be defined. There, I'll have to depend on you people to see what you can come up with. The third one is the cost of this business. It's frankly very expensive and getting more expensive. I'm sure this is more my problem to worry about than yours. But we have competitors who are getting very heavy subsidies combined with very focused activities to become major participants in this business. And these make the future of the U.S. industry less certain than I'd like to see it to be. The cost of capital in the U.S. is a lot higher than it is, particularly in Japan. The availability is less, and the patience associated with that is probably somewhat less. So anyhow, to summarize, I think technologically we're okay. We kind of see where that's going. The industry structure is going to continue to change. We'll get different players in these 5-year updates of who the biggest companies are and who the leaders are. That's something that happens in any area where the evolution is fairly rapid. It's hard to lock in a position for very long. Europe and Korea each have 2 or 3 companies that aspire to be in the top 10, to say nothing of the U.S. and that other 190 U.S. companies that are on there. They all hope to get there too. So there's going to be continued push to get dominant positions there. The markets are going to change in the world. Europe is either going to be more open or more closed depending on who you talk to with the changes from 1992. And Lord knows the changes of the last few weeks with looking in Eastern Europe are certainly going to have a tremendous influence on the way this industry and a lot of the rest of the industries develop. Japan, we keep hoping, will implement the intent of the trade agreement we have with them that's going to open their markets to U.S. semiconductors. It's happening very slowly. We're making a little bit of progress. And anyhow, it's a game for well-financed companies and governments in particular. But the important thing I want to leave you with is the market must continue to expand if we're going to maintain the spectacular rate of progress we've become accustomed to. And you can do more to help that than I can, certainly. And I'd be happy to take questions on anything that relates to the industry in general as well as what I've talked about here specifically. Yes?
Yes, what do you see as the future of optical chips, optical technology?
Do I have to repeat the questions here?
If you use this microphone, we should be okay.
Okay. The question relates to what do I think of the future of optical chips? I think there are several very specific places where they're clearly going to be important. Connecting things optically is just a marvelous way to do it. There are no ground loops, and you get rid of a lot of problems. I am a skeptic about optical computing, where you do much stuff on chip optically. I don't really see the advantages as being that great, and I see the technology as being darn tough to get to. You're competing with a very well-developed way of doing things when you try to bring optics onto chip. You get away from silicon, which is a very comfortable material, in order to do the optical emitters anyhow. I am inclined to think it's going to perform the peripheral interconnection functions, but it's not going to be that important in the main body of the computing. Yes?
When you were doing your financial numbers, were any of those adjusted for inflation, or were those all in real dollars at the time they were representing?
Those are all in real dollars. These things are changing so fast, it doesn't make a lot of difference if you do adjust them for inflation. maybe you get a factor of 2 out of there, but when you're talking 2 orders of magnitude, qualitatively the data is the same. So I just used dollars at the time they were spent.
Question.
Yes.
What do you see as the future of the specific hardware or what's on the chip? I mean, do you think we'll see more parallelism, little bunch of little CPUs on there together, or what's going to be on the chips themselves?
Well, clearly we're going to see those kinds of things. We stick a lot of parallelism on now, and as the software is capable of using it, we'll put a lot more. We have we announced a microcontroller this year that has 2 separate RISC execution units, and the logic to apportion a job to the one that's not busy and so forth. We can handle that kind of thing. A thing like a 386 essentially has a 286 built in the corner in order to execute the things that were written for the 286. It only takes a small portion of the chip. A 16-bit processor takes 20,000 transistors. You're working with a 1 million transistor budget, so you use 2% of the transistors to do that. One of our new chips has a RISC processor, floating point adder, floating point multiplier, graphics subunit, and you fill the rest of the chip with static memory for a cache to speed up the operation of the whole thing. So we can put as much on there as we can think of the software and the system requirement to use. And our recent processor design tends to be put as much function on as you can think of and fill the rest up with cache memory. I'd hate to think, though, that our 1 million transistor or 100 million transistor chips are going to be little processors with several megabytes of cache memory. I think that would be a very poor use of the technology compared with what would theoretically be possible if we can think of the right functions. Yeah?
The U.S. has pretty well dropped DRAM production to a very small level. Do you think that's going to continue, or do you think that we'll get back into the DRAM business and start competing actively with the Far East vendors?
Well, the industry is trying to make a significant entry into the DRAM business, this thing called U.S. memories that you may have read about in the newspaper. The users of DRAMs got very concerned last year about the lack of U.S. sources for DRAMs. They found themselves getting DRAMs from their Japanese systems competitors. The Japanese companies are all vertically integrated. The same ones that make DRAMs make computers. And the U.S. suppliers couldn't get the number they wanted and had to pay a lot more money than they wanted to. So they were very concerned in '88 about a U.S. DRAM supply. So the semiconductor industry, which is not very interested in going back in the DRAM business in general because the competitive situation isn't very attractive there for us, decided early this year that we would try to solve our customers' problems. And a group of companies have sponsored trying to set up U.S. memories, which would be a major company taking IBM technology. IBM makes DRAMs for internal use. Would take that technology on a factory-to-factory transfer and enter first at the 4 megabit DRAM level and then at the 16 and subsequent generations. And we're trying to get the users to step up and pay the entry fee for that. And the entry fee is pretty high. We want $550 million in equity and want to be able to borrow about the same amount. It's a huge startup with the idea of getting very rapidly up to speed. Well, we were looking to get this concluded by the end of the year, to either get everybody to put their money in or not. And some of the stories in the paper recently have said that a few of the companies that would be logical participants, like Apple Computer, for example, have opted not to do it. And unless we get almost all of those big users in, I don't think we're going to have the muscle behind it to make it happen. And I'm actually going to get a report on Friday from the guy that's trying to get us started. So I'm not as up to date on that as I might be, but I give it no better than a 50% chance right now of getting financed. Because this year you can get all the DRAMs you want at good prices. We have short memories, unfortunately.
How do you view the markets in other Asian countries?
Would you repeat that, please?
Yeah. The question was, how do you view the markets in the other Asian countries in connection with the 3 things to keep it going, you mentioned.
Yeah, in the other Asian countries other than Japan,
That's right.
the countries that are getting very active in the PC, for example, Taiwan in particular, but also Korea, these markets are more open to us. Taiwan, Hong Kong, Singapore, we have as good an access to as anybody. They are certainly turning out a lot of product. So far, it tends to be duplicative. You know, it's kind of clones of what's being turned out other places. They haven't really taken an initiative to develop new applications. They have extended the market, though, by getting the prices down on a lot of things, which is also important in getting elasticity. So we view that as very important. That's the fastest growing market area in the world for us right now. Yes?
Yeah, you mentioned the need for semiconductor industry of enormous capital and especially process equipment, and also you mentioned the need for big markets. Do you think there is a big future for non-very vertically integrated companies who want to be players in the semiconductor industry?
Yeah.
And another question, I'd like to link it. Do semiconductor industry executives in the US wish that the federal government be more involved in the support of that industry, especially investments?
Okay. In the first case, you know, I clearly think that non-vertically integrated semiconductor companies have a position. We're vertically integrated to some extent. We have a small systems business, but it's small compared with our semiconductor business. In fact, in the U.S., the converse has been true, and that the only companies that have survived in the semiconductor business are ones that are principally semiconductor companies. Where big vertically integrated companies, you know, the General Electrics, the RCAs and so forth, were participants, they found they had areas that were less risky to make their investment. Those of us who grew up on semiconductors don't have a place to run very easily, so we're dedicated to that business. Now, the second part of your question about the U.S. government. We are anxious to have proper support from the U.S. government. Now, proper support, as far as I am concerned, principally is one that, to use the cliche, keeps the playing field level. If we're in a situation where the U.S. Says we're not going to favor any industries, we're not going to do anything for any particular industry, and our trading partners say, we want the DRAMs, we want the VCR, and they subsidize investments to pick those off, I think that's the dumbest thing we could do. We just sit there and let them have all the industries they want. So I think where we're competing with something other than the regular economic forces, we have to have something that protects us from that. And Washington is not in general agreement on that yet. We got, you know, a little help here and there, but there are ideologies represented back there that says the free market will take care of everything. That's fine, except the world is not a free market. The U.S. is the most accessible market for a variety of reasons in the world. Everybody comes after the U.S. market, and when they do it with advantages that we can't compete with, I really think we have to be concerned. Otherwise, we're likely to lose all of our industries of the future and be stuck with some of the ones of the past. So we are actively trying to get our government to understand this problem from our point of view, with varying success. Yes?
What do you see as the major challenges and opportunities for improving the productivity and quality of semiconductor manufacturing?
First on the quality, that's an area where I don't think there is a real problem anymore. You know, the quality of our devices, the quality of the Japanese devices, in the eyes of the major users are equivalent, and we're continuing to improve them. There's a lot that can be done yet in improving the productivity of the semiconductor industry. That is the one place the Japanese really did a better job than us. They focused on manufacturing early. They are still capable of doing a variety of things we're not. They can bring a plant up from a bare field to an operating plant a lot faster than we can. for a variety of reasons. You know, simple things like their construction crews work 24 hours, 7 days, where we get 4.5-day construction weeks. So they can build a plant a lot quicker. They have an equipment supplier industry where when you're installing the equipment, you get all the technicians and everything come in with the equipment. One plant over there had 1,200 people from the equipment vendors working in it at the time the plant was being brought up. We don't have that kind of capability here. So developing that sort of thing is important. And I think there's tremendous opportunities in the manufacturing area in general that we still have to address. We're trying to, there's been a lot of emphasis in getting manufacturing to be something treated in the universities with some success in that. I hope that we solve these problems before we're put out of the manufacturing businesses. Yes?
Intel's had a lot of very successful products through the years. Have there been any dramatic failures that you'd like to comment on, and what were the causes of such?
Here's my $15 million watch. I keep this just in case we ever get an idea going into another consumer product business. Sure, we've had failures also. We've had failures of commission and failures of omission, both. We just, in the last couple of months, announced the shutdown of a joint venture with Siemens Corporation, for example, which was a major new computer architecture, had a lot of advanced features built into it, but was a closed computer system, required a phenomenal amount of software to get over the threshold, and the closer we got to it, the bigger the program became, and the further out in time the payoff was. We just decided we couldn't carry it through to fruition. That's one. The watch was an example of something where literally I thought it was going to be a lot of technology leverage in there, the silicon chip we made, the display and so forth. When we got out of the business, the chip cost less than the little push pins on the side of the case that are used for setting it. It wasn't a technology business at all, at least at that time. For an error of omission rather than commission, I turned down the idea for the PC a couple of years before Apple came into existence. And somebody came around and described this thing and the programmable device for a home computer. The only application he could think of was the housewife having her recipes there, which I picture my wife and a computer in the kitchen. I can't imagine anything that seemed more remote. So I didn't appreciate, the person doing this couldn't express clearly what he felt. And that's often the case with a new idea. And in my experience, I couldn't translate what he was saying to something that seemed important to me, so we missed it. We missed the engineering workstation for a different reason. We just never put the resources on it. We used to own the engineering workstation market because we sold these development systems with our microprocessors. We dealt with the right customer, we had the right kind of product, and we had to keep all our energy in getting that going. We talked about doing what has become the engineering workstation. We never got the manpower behind it to do it. So we got lots of examples of things we didn't do right. But we've done enough of them right that we've grown to be a fairly significant business in the meantime. You don't have to be right every time. You've got to be right enough of the times in this business. Yes?
What is your view about the analog VLSI, and what is the vision of the Intel N64 neural network chip?
Clearly analog functions are useful, but most of the world seems to be digital in the electronics field at least. I don't know quite where analog fits into the very complex stuff. We tend to put an A to D converter on the front end of something, D to A, but do everything digitally on the chip. It's the digital circuits that really take advantage of the high degree of complexity. Now, which product did you ask about specifically?
There's a N64 neural network chip.
Oh, okay, fine, yeah. That is an idea of potentially a new market. I guess that is an analog memory if you look at it that way. It's a weighting function for neural networks. We think neural networks are a very interesting alternative way to do computing, particularly things like pattern recognition, where regular computers don't do well. And we want to at least keep our finger in that and participate. We had the right technology to make a particular product there. We got a small research group that's following up where that whole field is going. We hope someday we can really pick some products out of it. Right now, it's not at all clear how big it's going to be or exactly how to get a hold of it. Yes?
Yeah, returning to the semiconductor business, or fab business, there's been a major shift in the supplier base for semiconductor fab from the United States, and in particular from the Valley here, to the Far East. Is that a trend that's going to continue, or is Intel and other semiconductor houses doing something to foster rebirth of
the equipment
industry?
in particular?
Yes, the fab equipment.
We're trying to. Again, this is an industry initiative in Semitech where uniquely we have some government support and support by some 14 semiconductor manufacturers that now has a budget of something over $200 million a year, most of which is devoted to trying to make our U.S. equipment industry viable. Some key pieces have been lost. The lithography equipment in particular, we've lost our position on very strongly. The U.S. industry has a real problem, and it is tremendously fragmented. It's a lot of little companies. They tend to be one-product companies. The engineer has a good idea, gets support, sets up a company, builds one product. If we decide we want to use the product, we have factories in 4 different states, in Israel, and we probably need the product at all of those places at once. We need service. We have a very difficult time depending on these small one-product companies for those things. I think this is a problem because as we get further and further away from the new equipment, it'll be tougher and tougher to stay technologically competitive. So we would certainly like to see we'd like to see, frankly, a more agglomerated industry, maybe a half a dozen fairly major companies that took on the various pieces of equipment, with small companies maybe getting started and joining the bigger companies, looking at it from my personal point of view, to really get them up to critical mass so they can service our needs and also can stay alive during the downturns in the industry. Because if the semiconductor industry is cyclical, we go up and down, the equipment suppliers are the derivative of that. And their business goes to zero when ours goes down. And they only start selling to us again when we start growing again. So they have to have considerable staying power to stay in those businesses. And it tends to be a lot of companies get established on the upcycle, and a lot of them disappear on the down cycle, which is a waste of a lot of energy.
But carrying just a little further, it seems to me that the small company model that you're talking about is the one in which innovation occurs, and the large company model, while it has the staying power and the resources, doesn't innovate, or innovates much more slowly. And how do you maintain the sort of growth that we're seeing without that?
Maybe a model that is something like the way the drug companies and the biotechnology industry are working, where you get these innovative little companies getting started, and then they get partnerships with the bigger companies who take a license to make the products in a certain area, something like that. There's no question that the little companies are a lot better at exploiting new ideas. It's been that way in the semiconductor industry as well as in the equipment industry. And there are a lot of good reasons for that. When you don't have anything else to do but invent, you invent. If you got a big business to take care of, that is pretty high on your priority, and it slows down some of the invention. The invention may go on, but the company doesn't necessarily take advantage of it. It's often likely to walk out the door and appear as a Macintosh rather than as something else. Yes?
What role do you see HDTV playing? Do you think that big government initiatives on that are called for? Do you think they'll produce anything? Do you think the whole thing's a big boondoggle? What's going to happen?
Oh, boy. I think HDTV was the wrong definition of the problem. In the first place, there's not a U.S. company, a significant U.S. company that wants to be in the HDTV business, per se. It's a consumer electronics product that all the big companies have been getting out So there's not a U.S. player to take that on. On the other hand, the way computers are evolving, they're going to look like HDTV with more memory down the road. And there are basic technologies that I would like to see strengthened in the U.S. You know, the high-resolution display technology is something I really think we're going to suffer significantly by not having a major participation in. That's the principal one I see there, but there are probably some other technologies. And they're not related to the TV part of it at all. It's just the information display, information processing. And I think in particular, the way the electronics industry went after Washington on HDTV was a mistake. They were asking for something they weren't likely to get, and they didn't really have the infrastructure in place to do anything with it if they had gotten it. So collectively, we're not beyond running off half-cocked to do something like that. But the U.S. overall really has a problem there, in that we are very poor at bringing technologies to the U.S. that already exist someplace else. We can hang on reasonably tenaciously to something we already have, and lose it slowly. But I don't want to sound just defeatist, but for us to go back now and say, hey, we're going to be major players in high-resolution liquid crystal color displays or something, where there are half a dozen Japanese companies with a significant lead, most of us don't have the stomach to take that on. I'd rather find someplace else where they're not yet in order to tackle a new business. And I think we're going to have to get over that and learn how to go after all the technologies that are necessary in the areas we want to play. But it's going to take a while for business to change to the point where it's willing to do that. And some of those things are tied up with the cost of capital and how patient your investors are, and a lot of other things. But it's also a basic inclination on the part of the U.S. industry.
Let's take two more questions.
Okay. I'll take one right here in front.
Modern microelectronics has made life a whole lot easier in a lot of ways. Calculators do our arithmetic for us, word processors double-check our spelling, cash registers compute change, and so forth. Is there a downside to that? Are we all turning stupid as a result? I've forgotten how to multiply. A lot of clerks I've met have forgotten how to compute change. Spelling checkers are making people forget how to spell. Is that something you worry about?
I don't worry about it at all. But I have the other problem. It takes me 4 times as long to balance my checkbook with the computer as it used to take me by hand. But I think knowing how to do long division was an important skill when I was in school. But I don't see why everybody ought to have to learn how to do that now. If you can get it out of a computer, that's fine, as long as the basic principles are understood by somebody. One more question there. Yeah.
Okay. You mentioned the high cost of maintaining competitive process technology. If you consider the timeline to develop the next generation of processing technology, what phases in that development cycle are the best ones to focus on for improvement, to reduce the time to develop that technology?
What one is stuck with in developing these technologies to a significant extent is how many information turns you can get. That is, you get a process about developed, you want to start a wafer, take it all the way through to the end, and look at that and see what you have to change to go back again. And the cycle time through the technology is pretty long. So you may have to do these things with 3 or 4 information turns. So if you can look at ways to turn that quicker, you can speed up the development quite a bit. It's an area we put a lot of energy in on, and there's still quite a bit more to do. Also, you want to minimize the number of end-to-end turns you need in order to get it. So we do what we call short loops, little areas where you can locally try to optimize it so you don't have to wait for this thing to go all the way through. I think those are probably the greatest leverage points that we have. Okay, well, thank you.